This is going to be a review of everything we've done Wednesday and Thursday together. We're taking away the word problem situation and just giving you the actual number. So 3 steps. First, to find or figure out if it is a arithmetic sequence. Then, if it is, write the recursive and the explicit. If it's not, state why it is not. So remember, arithmetic sequence, they need to have the same difference. So you want to look at what's the difference between these two. Okay, -8 plus 7 is 1. -1 plus 7 is 6. And if the differences are the same, then you know it's arithmetic sequence. So since it's a arithmetic sequence, go ahead and write the recursive. The next term is going to be the previous term plus 7. And remember, this fancy recursive writing is just, another way of saying, in order to get -1, right, this term, you have to take the previous term, -8, and add 7. -8 plus 7 is -1. That's all this is saying and meaning. Okay? And then go ahead and do the explicit. So explicit, you take the first term, the n-1, and the difference of 7, and you put it all together. So we got -8 plus our n-1 times our difference of 7. And of course, simplify that by distributing and simplifying. So 3 steps. Yes, is it arithmetic? Then write the recursive, then write the explicit. Now, the next one, as you'll see in a moment, is not a arithmetic sequence. So if it's not a arithmetic sequence, like for here, the difference is 3, and for here, the difference is, and so on. So here you can just write, well, it says, if not, explain why it's not considered arithmetic sequence. Then you just have to say, because the differences are not the same. So the differences are not the same. And just to let you in on what we'll be looking at as far as sequences go the next time around, this is not an arithmetic sequence because they're not the same. However, what happens if you take the difference of these numbers? 2 and 2 and 2 and 2 and keep on being the same. So it's a different type of sequence. That's called a I think geometric sequence. And if we had enough time and we spend enough time, you might figure out what the pattern of numbers are. These are not random numbers. Anybody see it by chance? 1, 4, 9, 16. What would be the next one in the pattern? And this is going to be the hardest thing when we start doing this more in depth. It's just trying to figure out what these numbers have in common, what's the pattern. Not just kind of making up random things, but really looking for something that's concrete. What's that?
Is it 25?
It is 25? 25, then what?
25, then 36.
36, 49, 64, 81. So if you look carefully, this is 1 squared, this is 2 times 2, 3 times 3, 4 times 4, 5 times 5, and so on. So it's kind of like, there's not like a set of steps I can tell you how to figure out what the pattern is. But once you get it, you realize, oh yeah, it's just that. It's something simple, but sometimes finding something simple is difficult. We tend to complicate it and look for something that's totally like, extravagant when really it's something basic. So we'll get to these at another time after we cover parabolas. And when you guys start graphing, when we come back, we'll start graphing quadratics. You'll find out that this is like the equation y equals x squared. 1 squared, 2 squared, 3 squared, 4 squared, and so on. here's another special type of sequence. It's not arithmetic, but what do you notice about these? What do you notice about the differences and the sequence itself? What's that? Don't overthink it. Yeah, the sequence is the same as the differences. 1, 1, 2, 3, 0, 1, 1, 2, 3. And if I found the differences of these, what would you get? 0, 1, yeah, 1, 2, 3. So all the differences are the exact same as the sequence itself, which, if you look this up, this is called a Fibonacci sequence. We've actually mentioned this. I don't know if you've seen like the National Treasure movies and stuff. They talk about Fibonacci numbers and the golden ratio and all this other stuff. So we'll look at those at some point after we've covered all the quadratics. And number 4 is just another one for practice. Number 5, we give you the explicit. So go ahead and simplify the explicit, but then work backwards and write the recursive. So we've always done, like, here's a sequence, then to recursive, then to explicit, but we want to be able to go from in any order, in any direction that we need to. So we can work this backwards, that'd be just as good. So trying to figure out, well, what does f of 1 equal if you have this explicit, and what would the recursive be? Okay, so you guys can fill in what those are and figure that out. Same thing on number 6. Here's the recursive. Go ahead and figure out what the explicit would be. 7, just more of practice. This is an arithmetic sequence. It just has a negative difference, right? So make sure you account for that in your formulas. Number 8, same thing. Figure out if that's same differences or not. Please don't say, "Oh, this is hard. I don't know how to do it because it has 5th grade fractions in it." You can still find out how far apart 1 is from 1/2 and how far 1/2 is from 1/3 and realize if they're the same distance or not. Okay? Don't overcomplicate it. Number 9. Here's the explicit. Fully simplified. Write the recursive. So again, what's the starting point? What's the difference? Now, usually, if you look at all the other explicits, there's always been a number on there, right? Like here is -15. There's always been a number. So what number should we use if there is no number given? 0. Yeah, it's kind of like a y-intercept. If we had a graph y equals 3x, well, that's the same as y equals 3x plus 0. You start at 0, go up 3 over 1. So you're using a lot of the same rules as you would if you're graphing when you're talking about explicit functions. So, yeah, no number given. Let's start with 0. Okay. So go ahead and finish the front. We're not going to have time for the back. Just finish the front. Get all 3 of them in chronological order. Don't staple them together. And just give them to me with your name on each one. And then you'll be done.